Hi, welcome to Plutus, and today we are trying to learn what are Haworth structures. Well, Haworth structures are part of your class 12 unit biomolecules, and they are more frequently being asked when it comes to explain the structure of your polysaccharides, disaccharides, etc. Today, what we'll try to learn is we'll try to explain what are Haworth structures, why they are used, and how we can effectively draw them. So first thing, what are Haworth structures? As per definition, Haworth structures are cyclic form of Fischer structures of sugar or saccharides that can explain the chemical properties of sugars. Next thing, in order to draw the Haworth form, first we need to represent the Fischer form of the sugar that we were provided with. The thing is, many of the sugars that we had, despite of having the carbonyl carbon, they weren't able to show all the characteristics properties of carbonyl compound. For example, reaction with the Skiff's base. So, this suggested that the carbonyl carbon in every single sugar that exists, they are not entirely free. So here, Haworth comes and suggested that the carbonyl carbon in this sugar molecule that I have taken, which is my glucose, it is double bonded. And the sugar that I am taking for this purpose, this is my second last carbon, and this OH is on the right. Such sugars on the when on the second last carbon the OH is on the right hand side, such sugars are called as your D sugars. And since this is a glucose molecule, this will be called as D-glucose. Now, this carbonyl group by resonance pulls the electron density and attacks this particular hydrogen. So when it attacks it, there are two different options. First, the OH can be outside of the ring and oxygen remains binded with carbon at the fifth position, CH2OH, H, and rest of the molecules remains unbothered, OH, H, OH, and H. Other option is I can have the exact same molecule, but the OH may also lie inside of the ring. May also lie inside of the ring. So let's first look at it. The cyclic ring that I have, first oxygen atom, second carbon, third, fourth, fifth, and sixth. So this is a 6-membered ring. Same is the case with the below one. Now, the sugars or the cyclic structure having OH on the outside of the ring, such sugars are called as your alpha sugar. They are called as your beta sugars. But if the OH is lying inside of the ring, such sugars are called as your alpha sugars. Since I have taken D-glucose, this glucose molecule will be now called as D. It will be called as beta D-glucose. And this one would be called as alpha D-glucose. Now, when it comes to making the structure of these molecules, let's remove this and all of it from here. First thing that I'm assuming that the OH is lying inside of the ring. Here I'm assuming that the OH is lying inside of the ring. This OH should be here, and this is my cyclic ring. So, first thing, make a 6-membered ring with oxygen being the first atom. 1, 2, 3, 4. So this is a 6-membered ring. Now marking the number of carbons. Carbon 1, 2, 3, 4, 5, 6. On the clockwise direction 1, 2, 3, 4, 5. Sixth carbon always lying outside of the ring, and it is always represented on the above of the ring. Now, In order to make the structure, you always need to look for that whatever the groups that are coming inside of the ring, they are always assumed in downward plane of this ring. So that means if I make the groups right here as here, the OH is in the inside of the ring, so it will be coming at downward of the plane. Then OH again downward of the plane, hydrogen downward of the plane, OH downward of the plane. Whatever the groups that are now left, they will all be marked above the plane. So for the first case, hydrogen outside of the ring. For the second carbon, it is again hydrogen. For the third carbon, it is OH group. For the fourth carbon is again hydrogen. But here, in case of carbon number 5, you'll find that H is lying outside of the ring, so it should be above the plane. But since carbon has a higher priority, it is marked above the plane since it is a much bulkier group. While the hydrogen will be represented inside of the ring because now we do not have any other choices. And this is the Haworth structure for your alpha D glucose. Now let's try to represent the structure of beta D glucose. In beta D glucose, the only option we have is replacing the position of hydrogen with OH. So here only the position of hydrogen and OH has changed. So here this OH will now move above the plane of the ring, while this hydrogen will come below the plane of the ring, and rest of the group remains exactly same as they were before. And since the OH is lying outside, it will be called as beta D glucose. So from these two structures, what we have realized that the alpha and beta sugars only varies at position of the OH group above or below the plane of the ring, and this is the only distinction between your alpha sugar and your beta sugars. For the next part, similarly, you can also use the glucose molecule, it's not glucose but fructose molecule, to explain the similar structure. OH, CH2, OH, OH, and this should OH. Here, the rest of the groups remains the same. I only have this portion, so it can make a 5-membered ring. Since it can make a 5-membered ring with the OH, I can draw it like this. Here, OH is on the left hand side on the second last carbon, so this is L-fructose, making the structure a 5-membered carbon. 1, 2, 3, 4, 5. Marking the groups 1, 2, 3, 4, 5. Carbon number 1, CH2OH, always of highest priority, will be marked above the plane of the ring. CH2OH, CH2OH. Then whatever is left, it will be marked. Now I'm assuming that here the OH is lying outside of the ring, that the OH I am forming, let's currently remove this one. I'm assuming that the OH group is here. Wait, it shouldn't be here, it should be here. Oxygen should be here. So here I'm assuming that the OH is lying outside of the ring. So here remember, CH2OH is of the highest priority, so OH have no other choice but to be here. Then if wait, not this, I need to look for CH2OH first. Sorry. If that's the case, CH2OH can be represented inside or outside of the ring. So let's assume CH2OH is inside the ring. If it is inside, the CH2OH will come downward while the OH remains in the upward direction. Rest, whatever the groups which are outside of the ring, which is OH, H and H, they will be marked above the plane of the ring. Last we have CH2OH below the plane, hydrogen and OH. Hydrogen and OH here, and this is the structure for, since OH is lying outside of the ring above the plane, this is beta L fructose because we started with L fructose, and this is how you draw all the Haworth structure. Similarly, you can make different variations with the D glucose, L glucose, fructose, and you can make alpha beta structures as well. So I hope you have learned how to draw your Haworth structures and there will be no more doubts. In case you have any doubts, you can add it to the comment section and we'll get back to you. That's all for today. Thank you for joining us.